Let's mute our microphones unless we have questions. Please mute your mics. So I want to go around to the three circles real quick and just see if we can identify one word in each definition that's worth highlighting, so that we can just keep the definitions really simple. Let's start with temperature. We took notes on temperature was that last week? Yeah. Give me a word that's highlightable for our definition of temperature.
Average.
Do you have your triple Venn diagram handy on paper or electronically? Highlight the word average. So then what would we do in terms of highlighting for our definition of thermal energy? Somebody besides Dylan, what should we highlight for thermal energy?
Total.
Total. Thanks, John. So one of the big differences between temperature and thermal energy is the idea that one is an average and one is a total. Temperature is average kinetic energy, thermal energy is total kinetic energy. And we use different units to express them. I'm pretty confident we know units of temperature, right? Like Celsius and Fahrenheit, and we could even go into the Kelvin scale. What units do we use to express thermal energy? Somebody besides Dylan or John?
Joules.
Thanks, Ava. Yeah, joules, Joules. So these are all things that you could consider adding to your Venn diagram or just highlight. If you still have yet to turn in a Venn diagram, this is a great chance to get it finished up and turned in. So let's bring in the idea of heat then. Heat's the one that we really haven't talked about a lot. And our lab today called Feel the Heat, well, it's going to be about heat. So what is heat?
Transfer of energy.
Yes, Preston, thank you. It's all about the transfer of energy. So if I'm highlighting in my Venn diagram, I would highlight the word transfer. And when energy is transferred, which way does it flow?
From object with a higher temperature to an object with a lower temperature.
Little choppy, Jake, but I think what you said is from hot to cold, right?
Yeah.
Good.
Sorry.
Better. Yeah, it's just a flow from high to low, from hot to cold. It's just like pressure. Pressure works from high to low. Energy flows from high to low when we talk about heat as well. And there's three ways that energy can be transferred, and we'll talk about those later this week. If anybody included the words conduction, convection, and radiation in their Venn diagram in the section for heat, that's the three ways energy gets transferred. So part of today's lab looks at that as well. So we got 25 of us here. We're gonna jump into the lab here in just a moment, but I'm curious to know if anybody has questions with the Venn diagram.
What is heat measured with?
Also,
Isn't it?
yeah, great question, Preston. That is also measured in joules.
Okay. Thank you.
Yep, excellent question. Any other questions? All right, so I'm gonna shrink my screen down and share. And I'm also going to use this time to hopefully just do another tutorial in the ways of submitting work. So it looks like there's a handful of us in this document. Feel the heat. If you want to right now, you can access this document by clicking on the link. And here's what I'll say. If you want me to fill in the table for you, I'm going to be filling this table in as we go. So you can wait to make your copy until after I fill this in. But if you want to make your copy right away and be an active participant and fill in as we go, you can do that as well. So remember, when we access a document, we click the link, you press make a copy, and then you're going to do all your edits in the data table and with your conclusion questions. And then when it's time to share with me, you click share, advanced, change, and then we need this second option, which gives you a shareable link. A lot of you are just going to the address bar and copying and pasting this, which unless you go through those steps that I just narrated through, it's not shareable. So please make sure you follow those steps to make it shareable with me, then I can comment on your work. Before we jump into this lab and gather some data, does anybody have questions on the Venn diagram, getting to electronic work, making changes, sharing, anything like that? All right, we're gonna head into the kitchen. I only see, looks like about 10 of us in the dock. How's that look? Can you see my stove? Okay.
Yes.
Yes. Okay, good. So here's what I have going on. I don't know if you took a look very closely. Some of you maybe did yesterday at these steps. This is a challenging lab because the steps are tricky. The headings in the table are tricky. So I'll try my best to narrate through it and tell you what I'm doing. We're not going to fill in this picture. We're going to fill in this table down here. Taylor, did you have a question or was that accidental?
Yeah, so I actually just made a copy of what I'm doing of that table.
Yep.
So should I just write it? I was just gonna write it down.
Yes.
Do I have to put it back into another doc or?
Nope.
Okay.
No, so if you've already made your copy, then you're going to have to fill in the data table as we go. If you're waiting to make a copy, I'll attempt to get data put into this table. And then after class is over, if you make the copy, what I add to this table should show up.
Okay.
Okay, so trial one, we're going to put a hot spoon into some cold water. So I've got 3 identical spoons. They all have a mass of 28.6 grams. Oops. So that's not a variable for us. All of the spoons that I use are identical. 28.6 grams. The other variable that I'm attempting to eliminate here is the amount of matter. So this next heading over is going to ask me to put the spoon into some water. And I want an equal amount of water to the spoon. So you may have heard me say this before throughout the year, but 1 milliliter of water is equal to 1 gram of water. So what I can do now is just say that I need to use 28.6 milliliters of water to match the mass of the spoon. And if anybody wants to fact check me at home, you can, but 28.6 milliliters of water is essentially 2 tablespoons. So I have a tablespoon measuring device here. And then I have a thermometer for measuring temperature. Unfortunately, it only measures in degrees Fahrenheit. So that's the scale we'll have to work with, but I think we can still prove some points. Any questions so far with the way the data table's been filled in yet? No questions. Okay, so a couple more things about my setup. I have a cooler here, a soft-sided cooler, so that any energy transfer that's going to happen can be somewhat isolated, insulated to what's going on in the cooler. And then I just have this little tray of a carton of milk cut in half that when I put the spoon and water together, it's going to sit in here. So there's good contact between the spoon and the water, because I want the energy to transfer between whatever is warm to whatever is cold. In trial 1, there's going to be a hot spoon and some cold water. So if there aren't any questions, we'll just go through trial 1. We ready? All right. So what should I do first? I think what I'm going to do, now you don't know this, but right underneath my computer is my freezer. And if the computer drops, it's because, oh yes, it's right on top of the freezer. So I'm taking out a cup of really cold water. It's, I don't know if you can hear this, but ice has begun to form. It's not completely solid, but it's really cold. I'm going to make the assumption that the spoon, there's a spoon in this water here, which is boiling water. I'm going to make the assumption that the spoon has become the same temperature as the water. And boiling water here at 3,000 feet of elevation in Missoula has a temperature of 205 degrees Fahrenheit. So we're going to just say that the spoon has also become 205 degrees Fahrenheit. And I'm not going to take the time to insert the degree symbol. And then this water that just came out of the freezer, it's not frozen solid, but it's, give it a little stir. It's very cold. Okay, that cold water has a temperature of 36 degrees Fahrenheit, so slightly above freezing. And now we're going to put them together. So I want equal amounts of water and spoon. So I'm going to take 2 tablespoons of this really cold water and put it into my assembly over here. And now, this is the tricky part. I got to fish this hot spoon out without burning myself. And in it goes. They're in contact with one another. And I am going to measure the final mixture. So while I wait on this mixture to level out, what's giving energy to what?
The hot spoon is giving energy to the cold water.
Correct. Correct. Hot always goes to cold. So I put a hot spoon in cold water, and the thermometer is done moving, and it leveled out at 58 degrees Fahrenheit. Trial 1 is done. Just to show you what happened here. And that spoon just came out of boiling hot water, but I can touch it now, no problem. It's because all of the energy, not all of it, but energy left this to go into the cold water. Any questions on trial 1? Add it to my other dishes to do. My other dishes to do. No questions on trial 1? So we're done with this cold water. I'm going to use that hot water for trial 2. Trial 2 is going to be the opposite. I got a cold spoon that I'll put into some hot water. So everything about the spoon is the same mass. So I'm gonna take another cup out of the freezer. It's a blue cup. Wow, that is cold. This cup has, I just want to show you, it has a spoon in it. And the spoon was sitting in water that just came out of the freezer. So just like before, I can measure it, but it's not going to be different than what I measured from the other cup that came out of the freezer. So we can just repeat that value, but it's just swapping spots. So now I'm going to place this cold spoon into some hot water, 2 tablespoons worth of boiling hot water into my assembly. Cold spoon goes in, and we'll monitor the final temperature mixture. Looks like I need another box to fill in there, but if you are following along at home, you can put 205 in that, well, next to 36. I'll do that here in just a second. I'm actually going to let this sit for a moment. I put that cold spoon into 205-degree water, and we're just waiting on the final measurement to balance out. Ooh, it's up there. Well above 100. So this time hot water is giving energy to cold spoon, and the final mixture is still really warm. 165. Now 165-degree water is really hot. I can touch it temporarily, but that's hot. But that's it. That's all the data we need to prove a bunch. We got a lot of dishes to do. Ooh. Spoon is pretty warm. Questions?
Is the cold spoon that went into the hot water have a greater temperature because had greater area of hot water?
Nope, the amount of water and the mass of the spoon are the same. I guess what I don't know if this answers your question or not, Preston, but what we need to assume is that this column right here is what both the water and the spoon end at. They become this temperature. So we're going to leave area out of it. We're going to say that the mass of the spoon and the amount of the water is identical.
I just don't understand why they're so drastically different temperatures.
Yep, it comes down to this question here, number 2. One of these things is a conductor. One of these materials is a conductor. One of these materials would be considered an insulator. In other words, one of these materials gives up energy or allows energy to flow through it really easily. It makes dramatic changes. One of these materials doesn't change much at all. Energy doesn't flow through it that dramatic or that easily. So I'm going to let you chew on that for a little bit. And we're going to discuss these conclusions on Thursday like we would in a normal class setting, where you get a chance to answer them. But I'm going to caution you not to turn this in, because if you turn something in, you're telling me that I'm ready for this to be graded. I'm going to caution you to not turn this in until after Thursday's live lesson, because we're going to discuss these, look at the data, maybe share some answers, ask questions, all that stuff. So you're more than welcome to get your questions filled in. I would just avoid turning your assignment in until after we discuss on Thursday. So the Think Central lesson that you did last week could be really helpful for getting ideas about what conductors and insulators are, so on and so forth. Any other questions that have come up? We got about 8 minutes left. We don't have to use the whole time. 27 people ended up showing up. That's pretty good. If you joined late and you missed anything, let me know if you have any questions. Don't see any questions in the comment section. So if you feel confident about the information that we gathered and you think you can get to some conclusions, then feel free. Otherwise, you can hang out for one-on-one questions or just less people around to ask questions. I'll hang out for a couple more minutes, but that's it for today.
Thank you.
Yeah, good job today.
Thanks.
Thank you.
You betcha.
Gracias.
Yeah.
Thank you.
Bye.
Thank you. Thanks.
Yep. Yeah. Okay.